So here we are in part two, and the goal of part two is to wipe out our coverage of relational algebra operators. We'll spend a lot of time writing relational algebra, and we're certainly going to spend a whole ton of time writing SQL. But this should be, what's contained in this lecture should be all of the operators that we need for the time being. We'll notice later that relational algebra, because it's a good modeling tool and because we need it, as I mentioned in part one, as that counterpoint to SQL, we need some way of representing these operations that isn't an SQL query. We will come back, we'll throw in a couple of minor operators later to allow us to analyze queries for optimization purposes and things. But for the time being, so for the next few weeks of the course, we just need to get through enough of these operators that we can write powerful queries and that we can model them with relational algebra. So just like in part one, we're going to use this familiar schema, and I think at the beginning of part one I said, hey, you can pull this up on your own machine, pull the slide up on the side while you watch the video, and that way there's no need to flip back and forth. And then I flipped back and forth the whole time. I still think that worked pretty well though, so I'm going to do that again. But you might want to pull this up so you can visualize the data that we're working with. And just in case it's been a while since part one for you, we're covering this set of operators. And let's see, so we took care of this. Took care of the projection operator. We took care of the selection operator sigma. And we also talked about these union, intersection, and difference operations, and those are standard set operations. And we mentioned this. Now, I'm going to spend a lot more time on Cartesian product today and on the joins, which I'm going to view as an extension of a Cartesian product. And then we'll talk finally about this, which is sort of extended notation, but we need it to be able to model this feature, which is very powerful in SQL and allows us to sort of overcome one obstacle that we left hanging at the very beginning of the course when we introduced SQL. So before we start, we got to ease in. We got to get back into the spirit of writing relational algebra. Before we start, we have this thing. This operator doesn't really do anything. So it takes a relation full of tuples and returns all of the same tuples. What it does is it makes a metadata modification. And we'll see that this is actually quite helpful because there are not only times that we have to do this, we have to rename our columns, but there are also times that in SQL queries we find it quite natural to make up new columns that are really some synthetic combination of other columns. So for example, adding two things together. We can use this operator as a clever way of introducing that formally in a relational algebra context. So the name of the operator is the rename operator. It is represented by the Greek letter rho. I'm going to keep calling it rho. And it does nothing to the relation's tuples. It makes a modification to the relation's schema. So it renames one or more columns. This is an example of an operator that we do not use the same notation as the book for. So I am using this notation here. This is my strong preference. This is not unique to the way that I teach the course. This is done by in other places as well, but it's not done by the book. I feel like the best way to rename a column is to say, here's your relation, and you would like the column to be called this, and here's its current name. So I write new attribute equals old attribute, to symbolize that I'm assigning whatever was in the old attribute to this new attribute I'm creating, and that's a rename operation. Now, the book uses a very strange representation, which is much more, I guess, relationally focused. So instead, in the book, it uses this sort of representation to represent the renamed set of columns, and I find that that is unnecessarily formal, and it really doesn't fit well with sort of matching up your relational algebra to SQL. It's sort of clunky. Some sources, instead of the equal sign, use this slash. I think back in part one I was complaining about how I don't like slashes and backslashes where they don't belong, so I'm not going to use that. I guess you can use this if you want, but please don't use the version in the book. That's going to be too confusing. We don't need the row operator very often. We'll see a few examples in these slides, including, I think, examples where it legitimately is useful, but often it's for aesthetic reasons or housekeeping reasons, so it's not needed too often, but we do need to make sure we're consistent when we do use it. So here's an example of me using it. So instead of calling this column price per kilogram, I've decided to call it the price. And you can see I'm using the assignment style notation to change the column name, and although it's an assignment statement, we do view that as a move, not a copy. So if I take this column and rename it, it no longer exists. Instead, this new thing takes its place. Now, the reason why that can be helpful is that when we work with things like joins, we'll discover that in some cases, for things that aren't natural joins, we end up with ambiguity in column names. And that can, if we deliberately want to keep two columns with the same name from different source tables, renaming them is one easy way of cleaning that up. So in SQL, you can use this directive as to indicate a rename operation. So price per kilogram as the price. And that renames the column. Now, what's annoying is one of these weird bits of baggage SQL has is that you actually don't need it. You can just write price kg the price. And SQL parses that to mean that there's a rename that you've done implicitly. I think in the spirit of writing readable code, we ought to write the word as. It's 2 extra characters. Give me a break. The computer has no trouble reading the query either way. It doesn't take any longer if you put the word as there, but it helps humans read it, and it's good to write nice, readable, maintainable code. So I like the word as there, although formally it's not required. And I even encourage people, if you want to in the back of your head quietly judge queries that you see that people have written without the word as, I think you can go right ahead and do that. So great, okay, we've talked about renaming, we've gotten back up to speed, now we have to talk about this. In part 1, I think I made a mistake when I talked about the capitalization of Cartesian product. I was thinking about something out of the concept of an abelian field. There are a few of these weird proper nouns we don't capitalize in math. It turns out actually Cartesian is one of them. I looked that up between recordings. So we do capitalize the letter C in Cartesian. So Descartes got his due after all. So the Cartesian product, we talked about this in part 1 briefly, but the Cartesian product of two relations is defined the same way as the set theoretic Cartesian product, the cross product. Which is, I've got this one relation that has n attributes, we'll call them a1 through an, and this other relation with k attributes. So each member of the relation R is a tuple with n things, each member of S is a tuple with k things. And the Cartesian product, R times S, will then have one column for each column in either source table. And notice that we're actually renaming the attributes to be to indicate their source. R dot A1, R dot A2. That's because maybe in a less symbolic context, it could be that one of the column names in S is the same as one of the column names in R, and we therefore have to disambiguate. So the attributes are this whole thing, and the set of tuples is, well, we take one tuple out of R, so there we go, we take a tuple out of S, and then we mash them together into this one big tuple. And we do that for every possible pair, singular, of tuples in each of the source relations. And as it mentions down here, this is done in SQL as well, but we typically use R dot, or we actually put the source relation into the column name to avoid any ambiguities. So you can think about it, this probably is the same interpretation you were given in something like Math 122. You can think about a Cartesian product as being computed by this sequence of nested loops. So just as a more intuitive, programmer-focused way of phrasing what a Cartesian product does. We loop through every tuple in one relation, and then for each one, we loop through every tuple in the other relation, and then concatenate them and output it. So one question, a question we've been asking about a lot of our relational operators is, we know that the result of this operator is supposed to be a relation. So do we have to do any work to ensure that? Certainly we're outputting tuples and the result has a schema, so it meets those criteria, but are there going to be duplicates? We need to make sure there are no duplicates for it to be meeting the criteria to be a relational operator. Or if there are any, we have to then, maybe modify our pseudocode here to include that in our model. And basically it turns out, so you should try and demonstrate this to yourself on the side, but it turns out that if R and S are relations, so if they come in with no duplicates, there will never be duplicates in the result. If for some reason these collections R and S do contain duplicates, then there could be duplicates in the Cartesian product result. But as long as they obey the relational rules, so will the result. So there's no need for extra processing to eliminate duplicates. And therefore, this can be done in sort of a streaming mode. We just loop through each tuple in R. For each one, we loop through each tuple in S and then output the result. There's no need to save up our results or to check if we've already output something. which is nice. Now that said, maybe we can observe that what this is implying, given that we're outputting, every time we hit that line of the algorithm, we are outputting a tuple. It's implying that the size of the result, if I have relations R and S, and so the size of R, let's say, is equal to P, and the size of S is equal to Q, that means that the size of the Cartesian product will just be the product of the sizes of the source relations. And that's a lot of stuff. If R has 10,000 things and S has 10,000 things, that's a lot of stuff. And so maybe we need all of those. But we're going to keep that in mind as we go on, that the Cartesian product does have a lot of stuff in it, and that arguably, if we don't need all of those things, if we're going to end up pruning down that set, we really shouldn't be generating the cross product if we can avoid it. So one fact of nature is that R times S always contains, assuming R and S themselves are relations and have no duplicates, R times S always contains P times Q tuples if R has P and S has Q. I want to demonstrate the cross product, but the tables we've been working with that maybe you have off to the side in some other slide, I could page up and find them, but those tables are so big that I can't actually display the Cartesian product. So instead, I've made these limited versions, products X and order contents X, that contain a big enough sample to actually demonstrate something meaningful. And we'll take a look at those. The Cartesian product of those is this thing, which is all over the place. It's a lot of rows. It's exactly the number of rows we expect. So 3 times 4 is 12 rows. But if we look at the rows, we'll notice that there's sort of anarchy in a lot of them. There really isn't any reason why all that data needs to be in the same place. So currently, all the operators we've seen work on single rows at a time. So let's look at a row. There we go. Product 1 is Apple. Order number 1000 contained product 3. Those are two apparently disconnected, independent pieces of information. Why do I have them all in the same place? Okay, product number 1 is Apple. Order 1001 contained product 3. Again, irrelevant. Why do I care? Why would I bother combining those two things? Maybe you can see there is something relevant buried in here, some interesting connections that are being exhibited, but a lot of rows apparently contain garbage. They contain something I don't care about at all. We'll see there are legitimate uses for the full cross product, but not usually for elucidating some connection between pieces of data. We'll see it does show up, and it's mostly for, for data analysis tasks. You often use it as a way of expanding a set of input data that allows you to sort of think of it as a two-dimensional table or something. As sort of put your data in spreadsheet form. The cross product can be helpful for that. But otherwise, if we want to illustrate connections between these tables, the way we would with a join, the cross product gives us the rows with connections, but it also gives us a lot of garbage. So we'll notice, for example, that this row here, product number 2 is a pair. Order 1001 contained product 2. Okay, that's actually interesting. That's saying order 1001 contained a pair. Great. We've actually managed to show a connection between those two tables by doing this. But a lot of those rows, especially all the ones with Apple, they don't tell us anything. And so depending on what you're looking for, you shouldn't really expect to find it as the entire contents of a cross product, although it might be buried in there because we're producing every possible pairing of rows between the two source tables. So to actually compute a cross product in SQL, and you'll see there's no actual example of that besides these hints because it won't fit in the slide, you have two options. And one option is if you list multiple tables in your from clause, then SQL says you want all of the rows from each of these tables. I've got no idea how to pair them up because you didn't tell me. You didn't say natural join or something. So I'm going to generate all possible pairings. And so R comma S will produce a Cartesian product, a cross product of the two things. I'm not a big fan of that for a couple of reasons. And one of them is I've seen a lot of carelessly written SQL, not usually from people that have taken database courses, but out there in the world somewhere, I've seen a lot of carelessly written SQL. For example, I've seen open source projects, web apps and things that contain some database code. Clearly, their focus isn't database stuff, but they use a database. And often they sort of backdoor in a natural join by using a cross product and then searching the result. And you can think about that, and we'll talk about it again in a minute. But if you took this result of this cross product, you could strip out all the rows that are irrelevant and keep only those rows where the product ID matches up on both ends. And that would work, but maybe you can appreciate the database generates a whole ton of data and then filters most of it out. And that isn't the best way of doing it. I've seen a lot of cases where people have written bad SQL. I'm going to use the qualitative term bad SQL for this, where they do a join by the back door by doing a cross product and then searching it. And it appears that maybe the people that wrote that didn't realize that there was a join operator. Now, interestingly, I mean, and there's a funny aside here about the way optimization works in compilers and things. Interestingly, database engines and their SQL optimization logic very likely know that. They know that you can use a where clause to search a cross product to get the equivalent of a join, and they might optimize that into a real join. So even though those people are writing bad SQL, the database can stay ahead of them. But I would say, although it's fine to write a cross product using this R, S, I feel like it seems to signify that the programmer might not realize that there's a cross product happening. So it's absolutely fine to do it. You can go ahead and do it too. You can do it just to be passive aggressive if you want to, because you know I don't like it. That's fine. But I think in the interest of writing readable code, because we don't usually want a cross join, we should write explicitly that we're using one to make it clear to anybody reading our query that that actually was our intent and it's not an accident. And so, in my humble opinion, oh yeah, okay, so the slides are being very diplomatic. They have to be you have to write slides in the third person. You can't say I. In your instructor's opinion, hey, I know that guy. My mother always said he was very handsome. I think it's better to write this. SQL gives us an operator called cross join, which does the same thing as the R, S. But then if somebody reads your query, they say, hey, you wrote the words cross join. I don't know what you're up to, but you seem to know what you're up to when you write that. I think that's a good idea. And so just like with the as earlier, it's nice to write readable code. And again, we can begin thinking at this level, maybe it's okay to quietly judge cases where people are, not writing readable code when it's so easy to do so. So we'll talk about this in a future video a bit more, and I'll post some notes about this. But it is significant that SQL select statements have all these clauses. We've already seen the from clause, that's this, and the where clause, and this unnamed clause that I'll just call the column selection clause. And it's important that those happen in some certain order. And the extra clauses I bring up at the end of this lecture will factor into that. So the order that things are evaluated is important to understand, because unlike relational algebra, where you can just put brackets to order things however you want, unless you use nested queries in SQL, you get this weird stacked order that isn't necessarily linear. So just because the column selection occurs in the text before the word from doesn't mean it happens first. In fact, the from clause is the first clause to be evaluated. So just to be clear for the time being, before we see the other clauses, we evaluate from before we evaluate where. And that means that in your where clause, you can add conditions that relate to the result of the from clause, which is, in this case, that cross join. And so I'm allowed to search the result that I had earlier, that would be this thing, by my product ID. I'm actually going to search by this one, productx.product ID. And we can see I do that there. Notice the use of the dot to disambiguate which product ID column I'm using, because there are two of them. It's also worth considering. So, for example, here, I have to write order contents x.product ID, just like I have to do this down here, because there are two columns called product ID. I don't know which one I'm talking about otherwise. You can write order contents x.order num, because the database engine knows what you mean there, but actually you are allowed to omit the source table in that case, because there's only one source table that brings in this column, and so there's no ambiguity. So you don't have to use the dot, but the dot is available because otherwise you'd have no way of disambiguating. And notice that I'm doing a lot of sort of liberal renaming here, because that, I don't know if this is any more readable, but it does shorten the column names a bit. And then I'm searching by one of those duplicated product ID columns. Now, in the result, I still have a lot of garbage. I mean, I would say this row here and this row here don't really tell me anything. They tell me two disconnected pieces of information. And what's significant is that if I go back to my full cross product and I look at these green highlighted rows, and I talked about this earlier, there are rows that actually do contain data about the connections between these two tables. In particular, one table maps product IDs to names, and one maps order numbers to product IDs. And if I match those up by product ID, the shared column, and you can be thinking back already to this idea of the natural join, if I match them up by their shared column, I get something useful. So if I filter the result of the cross product by the rows that have product ID on the left matching up with product ID on the right, then I get this, which is the result of the classic natural join operation. So I can do that. I can write my natural join as a combination of a cross product and the sigma operator, and that gives me the result, although I have to clean it up a bit. I mean, usually we don't like thinking about the sort. In the results of our joins, we just like to talk about the names of each column. We don't care about which table things came from. We don't even need the second copy of the product ID column because we know that it's going to match up. But we can do that. And although I just said that I discourage writing a natural join in SQL using a combination of cross join and the where clause, I really think it's a good idea to view a natural join as a restricted version of the cross product, because that way the cross product sort of gives us the mathematical foundation to define all the different kinds of joins. So just to, this is a formatting note. Because we might notice your relational algebra expressions can get pretty long and ugly looking, you're welcome to define extra variables. So we're not doing assignment statements here. We're using the arrow operator to make it clear that we don't mean like a comparison, but we're just saying, this is equivalent to saying let P equal product X times order contents X. We're not defining new tables. We're just doing this as a notational convenience. And you could use multiple lines if you need to, and it does tend to be a bit helpful for actually reading your relational algebra, because otherwise you end up with one massive line of stuff. So here I'm just saying, look, let's just call this expression P and then take P and filter it with this selection operator. And just like I mentioned, the slides say this too, let's use the arrow if we say let P be something, because equals does have a meaning in SQL, and in relational algebra it's used for comparison purposes. So now we're ready to define formally a natural join. And I just mentioned that what a natural join really is. If we go back, we first take the cross product, filter it somehow. We filter it to match up the columns that are in common, and then we clean up our column naming, because we know that there are never going to be duplicated columns because they would have been used as the join criteria. So we don't need the products X dot anymore. So I have these two relations R and S, and they have some columns in common. They have 0 or more columns in common, and I'll call those columns Z1 through Zm. And for the sake of convenience, I've decided that those will be the first columns of R and S. But because we know that the column ordering of relations is irrelevant, it doesn't matter which columns those are. But for notational reasons, I'll just say for the sake of this slide that they're the first M columns. And also implicitly, these other columns in R and these other columns in S are not in common. So A1, A2 up to AN, they are independent from B1, B2 up to BK. So I have those, and then I can define the natural join in terms of the cross product. So what do I do to get the natural join? Well, first I compute the cross product, and then in what comes back, I keep only those rows where the common columns match up. So Z1 equals Z1, Z2 equals Z2, and Zm equals Zm. And then I have to do a bit of housekeeping. So I want to keep only one copy of the columns in common. And I know that, as we saw from our cross product example, we get duplicated copies of the columns in common. Because I know they're always going to contain the same values, I don't want to have two copies of it. I want the join to look like its own table, as opposed to like something synthetic I've constructed out of other tables. And so I have this projection which says, okay, keep one copy of Z1 through Zm, keep A1 through AN, and B1 through BK. So that's it. Do not keep two copies of the columns in common. What's worth noting here, the reason why I think it's good to ground ourselves in this definition as opposed to just intuitively talking about the natural join, is that if we have two tables with no columns in common, then that would be the case M equals 0. So Z1, Z2 up to Zm, well, there's just no Z1, M equals 0. So all they look like this. We should still be allowed to take the natural join of two tables that have no columns in common. And we can, because this definition allows that. So this definition says, first compute R times S. Now, filter out only those rows that have all of the columns in common matching up. But there are no columns in common, so the condition for the sigma operator ends up being empty. And an empty conjunction, so a sequence of AND operations where there actually are 0 operands in total, is assumed to always vacuously evaluate to true. The same way that we would define 0 factorial equals 1. In general, mathematically, we define a sum of 0 things to be 0, but a product of 0 things to be 1. And you might know if you took something like CSC 355 sometime in the past that there is a strong connection between the AND operator, either logical or bitwise, and multiplication. In fact, if you think about zeros and ones, so a single bit multiplication, it is identical in behavior to logical AND. So 0 times 0 equals 0, 0 and 0 equals 0, 0 times 1 equals 0, 0 and 1 equals 0, 1 and 1 equals 1, 1 times 1 equals 1. So because of that analogy, it turns out that if you have nothing in your condition, and it's a sequence of subconditions ANDed together, but there's no subconditions because you have a degenerate case, the condition always evaluates to true. So, okay, that's a long, circuitous way of getting to this point, but we take R times S, we have no condition to apply, and then we project out, we keep one copy of the common columns, which don't exist, and then we just keep all the other columns. So it turns out that if you take the natural join of two tables where they have no columns in common, you just get the cross product. I didn't mention this earlier, but it's worth pointing out. The operator we use for natural join is this bow tie looking thing. And I like thinking about this conceptually as, we have a cross product, R times S, but we're closing it off. We are adding extra conditions on it on both ends. We're keeping only those things common to both tables. And so we get that bow tie operation. The reason why I think that's a nice intuitive way of viewing it is that we'll see later that there is something called an outer join, which has an open end of the bow tie. So one or the other end of the bow tie is actually left open to signify that it's a bit more relaxed than an inner join or a natural join. All right, so we can go back to our less formal definition for, like our more intuitive definition for the natural join, which is that the natural join R bow tie S, so that would be, again, if I join R to S with a natural join, it's this, is every tuple of that's in R times S for which all of the common columns agree. So what's nice about the natural join is that we don't have to specify the common columns. They are assumed to always be used as the criteria. And we get the nice advantage that the result looks more like a wholly, a sort of a natural table because each column only appears once, there's no weird duplicated columns, and there's no need for disambiguation for which subrelation, which of the operand relations I got a column from. So to be clear, just to emphasize this again, because it's going to show up, if you're watching this video during the midterm, you don't need to send me an email to ask if the question is wrong, if it's asking you to compute the join of two tables with no columns in common. That is a valid operation. It's weird, but it's a valid operation. Some things to think about, and you should try and justify these to yourself, but I want to skim over them. So the first thing is, if I join a table to itself, I get the same table back. As long as the original relation was a relation, has no duplicates, I should get the same table back. If I have an empty relation, then joining or cross-producting that with anything gives me back nothing. And if you think about it, the issue here is that if size of R is P, like before, and size of Q equals 0, we know that the size of R times Q is equal to 0 times P, which just equals 0. And that means that if I take the cross product of a relation and something that's empty, I always get nothing. And interestingly, the point below gives us an easy way of demonstrating that if this applies for cross products, the same must hold for natural joins. So we know that to get a natural join, we start with the elements of the cross product, and then we filter them in various ways. And if you notice, that means that there's nowhere after the cross product that we ever actually add tuples. And so the result that comes back out of the cross product, the sigma, and the pi has to have a subset of all of the tuples that were in the cross product. And that means that if you think about what the size of the cross product is, which is equal to size of R times size of S. That means we get this sort of triangle inequality. The size of the natural join is at most the product of the sizes of the source relations. And that is just a consequence of the fact that a cross product is always a superset of a natural join. And one reason why I like this definition, because it ties everything together and it sort of defines the cross product as the primordial join operation, the most basic and sort of useless for the most part, but basic join operation, and all other joins are refinements of that. So there's the natural join, just for the sake of completeness. And we know, well, okay, there's the natural join of our familiar tables. And we know that the natural join, if we have two tables that we know have some semantic connection, like products and order contents, the natural join contains useful semantic information. In this case, it's telling us the name of each product in each order. We know from before that we can compute a natural join in SQL using the natural join operator. And that is far preferable in my mind to attempting to do a cross join and search it. You can do that, but I feel like there are plenty of reasons why that's a bad idea, even if the database's optimization engine can catch on to what you're doing and fix it. It's way better if you have all these options, because we know SQL is a declarative language, like I said in part 1, to try and state as concisely as possible what you want in SQL terms, because the better you are at stating that, not just in terms of stating it correctly, but also concisely, the more likely it is the database can't just give you your answer, but give it to you quickly. So we have to, this is a topic we have to bring up. I mentioned we want to get through all of our notation in this lecture. We're going to have to circle back to it later once we've done more SQL, and we need to use the feature that this is actually modeling in SQL. So we're not actually going to talk too much about the SQL analog of what I'm getting to here. Basically, the natural join operator, compared to cross join and things, natural join is really restricted. Cross join computes every possible pair, which obviously is not desirable. Natural join computes a very specific pairing, where it's all of the common columns are matched up, and they must have identical values in all of them. Two particular tuples from R and S only get paired up if their values in every single one of the common columns is equal to each other. There are times that we don't want such a rigid condition, and there's a variety of reasons this could occur. So one of them, a pretty common use, is you only want to join on some of the common columns. There are some columns you would like to keep separate. You don't want to match up all of them. Natural join doesn't give you that choice. So this slide is helpfully reminding us that a natural join equals this thing that we just saw 3 slides ago. I guess our memory's not that short. We sometimes want to define an arbitrary condition, so not specifically this condition that we get with every natural join. Maybe I only want to use a subset of common columns. Maybe the matching criteria is different than the equal sign. Maybe I want to match them on the less than sign or something, which is a bit of a crafty thing to do, but we'll see a bit later if we're clever, excuse me, we can use that to subvert a lot of pretty difficult queries. We can come up with pretty concise queries to solve complicated problems if we leverage using clever join conditions. So we have this generalization of the join operator called formally a theta join. And so theta in this context is some condition. And we actually see what's happening is I'm providing the condition to use on the sigma. And actually in SQL, I will just keep calling this thing inner join because it tends to manifest as an inner join. There's also something called an outer join, which isn't really covered by this, although it's similar. Like it's a type of theta join where, an outer theta join would look like this. So I can still put a theta on an outer join, but we can't talk about outer joins until we know about stuff like empty or null values. There are times when a theta join can be so complicated that you actually do have to model it with a cross product and searching. But generally speaking, you can model it in SQL with an inner join. And so we would write it as R bow tie theta. So there's my bow tie. And then I stick some condition down here on S. And it's equivalent to doing a cross product and then searching it with sigma. But again, the equivalence in relational algebra doesn't imply equivalence in SQL. It's still better to write the theta join operator because your database engine may not understand if it sees this construction that what you want is a theta join. It might do everything the long way, where it generates the cross product and then searches the result. So for the time being, let's just think about theta join as being this combination here. And then we'll worry later about how that fits into everything else, because we have to spend some more time building up some fluency in other parts of things like SQL before this really has much meaning. There isn't much use for it in the small data set that we're already working on. So then there's this. I talked about this in part 1, the fundamental set operations, how they apply to relations. We want to come back to that, though, because we've now seen a bunch of new relational operators. We've even gotten to things like joins. It turns out that, obviously, if we expect that there is this correspondence between relational algebra and normal set operations, we should have that in SQL as well, if they're so useful. If we're modeling relations as sets, clearly there's some reason we're doing that. So there are set operations in SQL. And it's weird because although they work exactly as you expect them to, where you can use them is oddly restricted. So in SQL, you can write things in the from clause. You can write R natural join S. And natural join, as its operands, can take tables. But they can also take, I could actually do natural join select and then have a nested query. I could have the operand of the natural join be an actual physical table or the result of some nested query, which we expect because the result of a query and a table that we take off of disk are both relations. What's weird is that because of the way SQL was defined, and I haven't really been able to come up with a good answer for why this is. I think it's just some historical baggage that we have to live with. Because of the way SQL is defined, we can't place the word union in all the same places we can put the word natural join, even though both union and natural join are fundamentally binary operators that take relations as their operands. So here's an example of a union in relational algebra. It's exactly what you expect. I use the union symbol like I would in set theory. So I'm taking first all of the products whose price is less than or equal to 3, and then separately all products whose price is greater than or equal to 6. And I'm taking their union. And you might notice the result is semantically equivalent to a single sigma operator where I have price less than 3 or price greater than or equal to 6. There's never any worry of there being duplicates in my result because the union is a set operation, and therefore any duplicates, anything that happens to be in both halves of the union will show up only once in the result. In SQL, I do this. Notice the funny position of this operator. It's not in the from clause. I apply the union operator to two fully formed selects. And what's sort of odd about that is that SQL considers this entire thing, everything before the semicolon, to be a select statement, even though you see two select statements inside. And actually that's because SQL also considers this to be a select statement. So those of you that have taken 320, this is one of the miracles of context-free grammars. We have select statements defined sort of recursively based on whether an operator appears or not. So what I'm doing here is I'm constructing the relation produced by selecting from products where price is less than or equal to 3. I'm taking the union of that with the result of selecting from products where price is greater than or equal to 6. I'm not allowed to use union inside the from clause like I am with a natural join. I have to use it with fully formed select statements as arguments. Now that said, I am allowed to use it inside of, like it doesn't have to be appearing at the outermost scope. I just have to make sure that its two operands are always fully formed select statements. So I could write something. I could use union, for example, in a nested query, as I've done here. So it's perfectly fine to use union or the set operations inside of nested queries, but their operands have to be fully formed selects as opposed to just table names. Here's an intersection. Give me all products that are less than or greater than or equal to price 3, all products whose price is less than or equal to 6. Now give me everything in both of those sets, everything in the intersection of those things. And again, duplicates, of course, have to be eliminated because I'm doing a set operation. And so in SQL, we use the word intersect for this as opposed to intersection. So be careful. If you get a syntax error, it's because you probably wrote intersection. I've noticed that the funny, not only a location of the operators in SQL, but also their funny names seems to mean that people have less comfort using them. So a lot of times I've seen people tie themselves in knots trying to write a query but not use set operations when a couple of set operations would have made things dead easy. I think that's because people take some time to develop comfort with them because they have such strange syntax. So please try and get used to them. Try running a few set queries as soon as you can. Just copy and paste the ones from the slides. They can be really helpful to use. And they, just like natural joins, are one of these things I've noticed a lot of SQL out there in the wild, written by people that aren't really database people. For whatever reason, they don't learn them, and so they write these really tangled up queries that can often be slow and hard to read because they don't know about features like this. Or because of mythology that's been around for 20 years about, oh, you shouldn't use intersect, it's really slow. Well, it might have been really slow on one database engine 20 years ago, but we expect if we have operations, the database engine should be able to execute them. So set difference is this. I mentioned, I think, in part one that I like the minus sign instead of using weird, like a backslash or something. So this is the difference of those two subqueries that I already talked about. And in SQL, it's the word except. So this is another one of these weird issues with SQL, this strange baggage. So I think the issue here is that I would call this operator difference because except just comes out of left field. Maybe they thought, but wait a minute, we already have a minus sign, which we use in arithmetic, so we can't say difference because that could mean that. I think the interpretation here is select all the tuples meeting this criteria except those tuples that meet this criteria. So they mean it in a sort of like the use of the word except in English. I think in a more modern language, we've evolved over the decades since SQL was invented, this base, like sort of best practices for how to name things. I think it would probably be called, the operator would be called something like, something technocratic like set diff, which is fine. I don't like the name except because, again, it's hard to remember. But, you know, they tried. They tried to come up with something. They had a vision. There's some romance in it. Set diff just feels sort of sterile. But that's what you get these days. That's something we have to live with because SQL, again, is a pretty old language, and it was designed before a lot of our modern conception of what an intuitive set of operators looks like. So that brings us to this. We actually now have seen all these operators that they work with throwing tuples out of a relation, modifying the columns, searching based on specific rows. But we still have this problem of needing to ask questions that require more than one row at a time. And all of the operators we've seen look at each row in a vacuum. So they ask questions like, is this row in or out? Or they take each row from one table and rows it from another table and mash them together. But at no point do any of our existing operators look for or look at multiple rows in the same table. I suppose except maybe at the end if they're eliminating duplicates or something. So at the very beginning of the course, and the point of things like normalization and ER modeling was don't worry about having multiple tables. Don't worry about not storing contingent data like the total cost of the order. If you keep all the source data, you can always get what you want. So how do we do that? Clearly, if we've been building up to having this normalized schema and only storing basic data, how can we get interesting things out of it? It's reasonable that if this data system is going to do anything for me, it shouldn't expect me to have to pull all the data out to ask questions like what was the cost of each order. I should be able to frame that in terms of this relational algebra, and I can, but it requires one more step, and it's going to require some notational ugliness, I think. So I want the total cost of every order. And as things currently stand, I don't even have the total cost of each item in the order. I have the items in each order and how much I purchased. And over here, I have the cost of each item per kilogram. But I know that I can do a join to associate those two things. So here, I have joined together products and order contents. So I have the price per kilogram and the kilograms bought in the same table. And I observe, I can easily use those two things inside of each row. So 5.0 times 0.6 equals 3. 5.0 times 10 equals 50. I can use the internal contents of each row to compute the total price of each item. So the price multiplied by how much of it I bought. And so I can actually add, in SQL this is dead easy, I can add a new column containing that synthetic value. This is a case where I could use the rename operator to give me a new column. I can rename the synthetic quantity price times kilograms bought as item price. So that's one way of modeling that with relational algebra. And I do that based on the result of this natural join. Great, okay, so now I've got the total price of each item. What I want, though, is the total price of each order. So order number 1002 costs $220. and order number 1000 costs $3. I want to compute that final number. I don't want to have to look at all these rows to figure that out. So what I want is to add up a bunch of things in a restricted setting. I don't want to add up the item price for everything. I want to add up the item price for everything whose order number equals a certain value. So actually, Jake, just to go back, this relational algebra here is modeled by this SQL statement. Notice how we see the word as, just like I mentioned earlier. We're writing a nice readable query to rename price per kilogram times kilograms bought as item price. So I have this. What I want is to basically batch up rows into groups. I want to go through, I want to decide what criteria I'm going to use. I mean, I could ask a question like, what's the total cost of each order? But I could also ask a question like, could you tell me how many dollars worth of each product I've bought? So, I mean, in this case, here's rows that use product 3. And so there is I have purchased $68 or there have been $68 of product 3 purchased overall. So I want to, based on some criteria, which may not always be the same, so it's defined by me, I want to go through the rows in my table and I want to toss them into buckets. I make a bucket for everything in order 1000 and I toss each row into that. I make a bucket for order 1001 and I toss every row that has that characteristic into that bucket. And then a separate bucket for order 1002 and a separate bucket for order 1003. Once I've put them into buckets, I want to perform an operation on all of the rows in the bucket. So I want to do something like within the bucket for order 1001, add up item price. Within the bucket for order 1002 and within the bucket for order 1003, add up item price. So this is a two-phase process. I want to group my rows, and so put them all into buckets based on some criteria. And when I do that, the assumption is what I get out of this will be one result per bucket. So if I make 4 buckets, whatever table I end up with will have only 4 rows, one for each bucket that I ended up with. So that's the grouping phase. The second phase in this process is I need to find some way of boiling down all of the stuff that ended up in each bucket into a single output. And so we'll call that aggregation. So I have to define some operation that operates on the entire contents of the bucket and produces one answer. So this is 2 phases, but you need to have them both present at once. Generally, you wouldn't have grouping without aggregation or aggregation without grouping. If you do, what you end up with is a sort of trivial form of the other half. So if I have grouping, but I don't specify aggregation, then what I end up with is just figuring out how many distinct orders I have, basically. I figure out how many buckets I end up with. If I have aggregation but no grouping, then SQL will interpret that as use one big group of everything. So the grouping still happens, it's just implicit and it defines the group to be everything. So here what I want is to go from what I had originally, which is this table giving the total price of each item in each order, to this, which is giving me the total price of each order. So notice that what I end up with is an aggregate quantity, so adding up the cost of each order, so the contents of each bucket, and whatever my grouping criteria was. In this case, my grouping criteria was order number. And a key issue is, if you perform grouping, the only things you're allowed to take out of the bucket are direct values of the grouping criteria, because you're guaranteed, if I say, give me the order number for this bucket, well, everything in that bucket has the same order number, so it's consistent. But I'm not allowed to say, okay, for order 1003, I want the product ID. Okay, but what do you mean? What product ID? There's 3 of them. You want the product ID? There isn't one. I don't know what to do. And so in this case, the only thing you're allowed to take out of a grouping operation is either the criteria, which we know if I say give me the order number, there's only one of them, or the result of actually performing an aggregation operation. So I could say, don't give me the item price of group 1003, because which one is it? Is it this? Is it this? I don't know. But I could say, give me the sum of the item prices. Aggregate them into a single value. You have to specify how to turn the contents of the bucket into one final value. So in this case, my aggregation would be, I want to take the order number out of each bucket, which is consistent, and I want to aggregate the item price attribute by summing them together to create the total price. And so in SQL, that looks like this. I'm going to read it from bottom to top. So first, I compute my natural join as I did before. Great. And then I group by order number. So I'm going to group by the order number. I am allowed to say group by more than one column. Just like a join, if I use multiple columns, it groups by the collective values of all of them. So there's a bucket for every possible combination of my grouping columns. So I group by order number, and that creates a bucket for each different order number that's observed. In this case, there are 4 of them. And then up here, I select order number, okay, and then I select the sum. This is an aggregation function, the sum of the price per kilogram times kilograms bought. And I call that result total price. Inside each bucket, I do have price per kilogram and kilograms bought, and I multiply them together and then add up all of those products to get my total price column. So sum is an example of an aggregation function. You can only use it with grouping. If you use it with no group by clause, it will assume that the group you're talking about is everything in the relation. So here's some other aggregation functions. We've got sum, min, max, average. There's count, which is count the number of values that a particular attribute has inside of a group, which is, it's an odd way of phrasing it. It's counting the number of not necessarily distinct values. That sounds, so if I used count on this, if I said count item price, well, okay, it would count 1, 2, 3. But even if this was also equal to 15, it would count 1, 2, 3. It counts the number of times a row has the item price attribute, whether or not it's already been seen inside the group, so 3. You might notice that and say, wait a minute, isn't that just counting the number of rows in the bucket? And the answer is almost always yes, except in a case that we'll get to later, and it involves null values. If you actually want to always count literally the number of rows, use count star. That's just count all the rows in the bucket. There's also this strange option, and people that are used to other languages might be screaming internally looking at this. Count distinct attribute. And you think, why can't we just call the function count distinct? Why do we put the word distinct just suddenly inside the brackets for the function? And just like the word accept, this is the interesting, they've tried, the romance of it. They've come up with some clever way of writing it. It's infuriating, but hey, they tried. So what this is saying is take this attribute from the rows inside the group, eliminate duplicates within that attribute. So count the number of distinct values of that particular attribute inside of the group. And you actually can use the distinct keyword before the attribute elsewhere as well, sum, distinct, or whatever. So it's an operator. It's just that it can't be used in a lot of contexts, but it can be used inside of most of these aggregation functions. So how do we write that out in relational algebra? There is an operator called gamma, the aggregation operator, and it doesn't seem as if anybody can really agree on how to do that. I'm going to use this notation. If you look at what the book uses, you might agree that this is pretty similar. It's got a couple of tweaks. I think this is closer to the way people tend to view this thing mathematically than what the book uses. So we will use this. This is the canonical source for the gamma operator for this course, this slide. We'll also see that different database engines enforce how SQL handles grouping a little bit differently as well. So we'll talk about that in a second. My gamma operator looks like this. It takes some relation R, and it's parameterized by 2 things. The set of grouping columns, which I put on the bottom, and one or more. So I'm actually allowed to put F and then comma G of whatever, but one or more aggregation functions on the top. And the aggregation functions take as their arguments any of the columns in the original relation R. And so what comes out of the gamma operator is a new relation that has as its columns the grouping columns and that's it. Nothing else comes out of there. If I want certain columns in my result, I have to get them through aggregation or using them as grouping columns. Anything else in my original relation R is not visible. So I mentioned that earlier. It's because if I say, give me, I'm only get one row for group 1003, give me the kilograms bought. Okay, but what is that? Is it 3 or is it 4? You didn't tell me how to reduce that down to one number, so I can't do anything about it. If you want, let's say, the average number of kilograms bought or the sum of the kilograms bought, use an aggregation function. So what's weird is that in SQL, so Postgres, if you attempt to violate the rule I just described, it gives you an error. It says, I'm sorry, you're not allowed to use, there are no columns that come out of the aggregation besides the aggregation functions you used and the results of the grouping operation, the grouping columns. SQLite does let you pull out arbitrary columns, even ones that should have been that aren't well defined because they haven't been aggregated. And so don't do that. In general, your queries are, in this course, regardless of how they work in SQLite, they are incorrect unless they enforce the rule that's stated on this slide, which is also enforced by Postgres, which is our primary database server. So here's a way of writing the query I was doing earlier. So that's this version, not the SQL version. Here's a way of writing this query in relational algebra using my new gamma operator. Notice that I'm using multiple variables here just to try and spread everything out. So first I compute the natural join, then I rename my column to create the item price column as before, and then I take the result, feed it into the gamma operator using order number as my group by, as my grouping criteria, and then I say, as my aggregation function, use sum of item price. And I sort of sneak in a renaming operation there. That's fine. Because the alternative is, if you don't rename the column to total price, if you just have it the way, like if it looks like this, then the name of the column is the clunky sum of item price, which is hard to work with. So giving it a new name is perfectly fine in the gamma operator. I think that's a great notational convenience because in SQL you do typically rename aggregation results to have their own column name. Now, just to be clear, you may have noticed in the earlier slide where I gave the result, there's no mention of an item price column here. Instead, I group by order number, and then just swiftly from that, I multiply price kilogram by kilograms bought, and then take the sum of that. For the sake of making sure we understand the difference, I am allowed to create an item price column. I'm allowed to do this relational algebra directly in SQL. What I have to do, though, is first I have to perform a nested select statement that creates the item price column. And then outside of that, I group columns in the result and take sum of item price. The reason why I need a nested column is because in this version, think about where would I create the item price column? Well, I'd stick it somewhere in here. I'd say something as item price. But the column selection clause isn't done until after grouping. By the time I get to that point, it's too late to create item price because grouping has already been done. That's sort of evident because if I'm doing aggregation in my column select clause, it means that grouping must be done because how could I aggregate without groups? And so it turns out that there is no point in this query where you can create item price if you need item price to perform aggregation. And so instead we have to create it in a nested query and then use it on the outside of the nested query, which is still fine. And in general, we shouldn't develop a phobia of nested queries. One of these other weird bits of mythology is, oh, don't use nested queries. They might be slow. Well, yeah, everything might be slow. The reason we have these features is to use them. Let the database engine figure out how to make things run fast. Generally, there are queries that run slowly, but until you see one, don't worry about making it run faster. So I'm allowed to, in this case, because I've done this this nested query, this is a different nested query, I perform the aggregation and grouping like I did before in a nested query, and then I look at the resulting relation as in this outer select statement, and I can filter it. I could select all orders whose price is greater than 100 by doing that, by adding this where clause. But to be clear, the where clause in a select statement is executed before any grouping happens for that select statement. So you'll notice here the where clause that I have, the statement it's in doesn't actually have any grouping. There is grouping happening, but it's happening inside this box, inside this nested query. If I have grouping and a where clause in the same query, where happens first. So the where clause is a way of throwing away certain tuples before you group. So if you want to filter tuples after grouping, you either have to do a nested query like this, or leave it up to the SQL people to come up with a peculiar way of working around this. I don't think a modern language would do it this way. They just said, we don't know what to do here, throw in another clause. Throw in a second stage of the where clause, and it's called having. So the where clause happens before grouping, then we do grouping and aggregation, and then the having clause we can use to throw away tuples based on the result of aggregation. So here I'm saying group by order number, keep all the tuples having this sum be greater than 100. And you'll notice that although I rename this as total price up here, it turns out that the having clause happens before any of this. So although I do eventually rename the column to be called total price, there is no total price column at this point. So I have to use the raw sum of notation. Here, the total price column does already exist because I created it inside my nested query. And so, although, and this is a case where, first off, on the coming assignment and things, just use nested queries if you want to. Don't worry about any performance things. It is true as time goes by that, yeah, the having clause does have some benefits, and databases often are much better at optimizing if you use where and having, as opposed to using where and then where again on the outside of the query. But for now, follow your dreams. Keep using the where clause if you like the where clause. If this logic of making a nested query appeals to you, and it often does to people because it does fit the sort of recursive mindset that most computer scientists have at this point, then just go ahead and use that. Don't worry about memorizing all the arbitrary clauses. Now, you'll be expected perhaps to see SQL queries that use the having clause in this course, and over time it probably will become less scary to use it. But if you want to use nested queries, just go ahead and do that. So, at this point, we've actually seen all the operators we need from a relational algebra perspective. We probably need some practice writing relational algebra, and we certainly need some practice working through applied SQL examples. So I'm going to post some separate videos. One, I'm going to post sort of a demo of all the database software that we can use, and then I'm also going to post a bunch of videos that basically consist of me going through database exercises, SQL and relational algebra, because that's how I would normally do a course like this at this point. We just write some code and talk about it. So I'll post some videos, and then we'll also have, I guess by the time you see this, I've already announced them, some more of these live tutorials where we can actually talk about writing queries and things between now and the assignments and the exam and stuff.